to have Hongbin Sun here. He'll be telling us about subgroup separability of free manifolds and its applications.
Thank you. Thank you for the introduction, and thanks for having me here. So I will talk about something really about fundamental groups of free manifolds. And that's it. Okay, let's first assume all groups are finitely generated. So in the talk. Yeah, so sometimes I will not, and I just say a group, that means it is finitely generated. And let me first talk a little bit about lerfness of groups. So if you were here last week, you have already seen it from Michelle's training course. And basically what I will do is repeat what she has told you. So let me start with the definition. And we have a group D and a subgroup H. We say H is separable in D if you take any element not in H, but of course in D, then you can find a finite index subgroup G prime such that it contains H, but this element G does not contain H. So you can look at this small picture cartoon. This is our group D. This is our subgroup H. And you take any element out of it, then you can find this G prime that has finite index such that it separates H from D. So separates this H from this small D. So this is what it says. So it is everything is, as long as you have a student who has taken basic abstract algebra for maybe a few weeks, then this is something he or she can understand. And of course, this definition has a lot of equivalent forms. You can also say there's up to here, you have a homomorphism from G to a finite group so that the image of D does not live in the image of H. Or you can say H is the intersection of all finite index subgroups of G that present it, and so on. So there are several different ways to talk about it. And then we say a group G is lerf. It is a shorthand of locally extended residue finite with a long name. If any finitely generated subgroup is separate. So I will emphasize this H must be finitely generated. It is part of the definition. To erase it, perhaps it's okay for today because I assume this, but in general, there are two different things. Okay, so this is all in group theory, but I'm a stream manifold topologist, so I want to see some kind of pictures of topology. So here is the intuition, which, intuition sometimes may not be correct, and this is not a 100% correct intuition, but it is basically correct. It's less a bit. So here you have some S, you have some map to something called M. And let's assume this S is compact. I didn't say anything about S. I guess in my mind, this is a manifold, but maybe it's not, who knows? And if J star of pi y of S is separable in the fundamental group of M, then what's the consequence? The consequence is that you can find a finite cover M prime, and this is a cover lifting property. If this group is contained in the image of M prime, you can do a lifting, and you want to do a lifting so that it is indexed. And I guess separable just means such an M prime exists. So I guess in my mind, this S is probably a circle and M is a surface, or maybe S is a surface and M is three manifold. These are everything in my mind, but you can think about some other thing if you want. And this is definitely not exactly true, but it is true in certain cases. So this is intuition, but it's less a little bit. Let's put them on. So this is intuition. And here's a summary of what groups are Lerf and what groups are not Lerf groups. Of course, I will only give you some examples, which is definitely not comprehensive. Lerf groups, at first you can take all finite groups, because here you can simply take G prime is just if H is, here I didn't say something. If H has a finite index, you can always take G prime is just your H. Then you are done. And if you have finite group, everything has finite index. And abelian group, this is exercise. Again, under the assumption that you are finite intelligent, you have classification, you can do everything. And yes, maybe let me. Next one I want to write down is polycyclic group. This is proved by Mosef in 1948. And then three groups by Hall in 1949. Yeah, so I guess this three group thing is actually you can find. So in chapter 1 of Hatcher, there's an exercise which more or less shows three groups are Lerf. Of course, Hatcher didn't say that. But the conclusion of that exercise that it is equivalent to this. And surface groups, by Peter Scott in 1978, and also Seifert three manifold groups in the same paper. So if you don't know what a Seifert three manifold is, basically a circle bundle over surface. Okay, then what's next? I believe there's definitely something between 1978 and the next thing I want to say, but that is the last thing I want to say in this list. Hyperbolic three manifold groups. That's proved by Ego in 2000. It really depends on when it is put in our archive or when it is published. Like it is around 2012 or 2013. And also, it's definitely also, at first, Ego proved something much stronger called what was special. Hyperbolic three manifold groups are virtually special, and you have already heard about it, and it implies so many fantastic things. But at least for today, let's only talk about them. And also, this result really relies on a lot of other works, include Danny Weiss, Stephen Manning, and Daniel Groves, and again, by the other things, Karl Markovich, and so on. I will not list all of them here because this margin is too small. Non-Lerf group, so probably the easiest thing to write down is that the free group cross itself, to do the direct product, and you have seen, probably you have seen it in Martin's talk, and I believe you must have a infinitely presented subgroup to make it, to get such a thing. Let's take a counter example. And as far as I know, it is proved by Alembi and Grothendieck in 1973. And by the way, I guess Lerf is really something. If you have if a group has a subgroup that's not Lerf, then your group is not Lerf.
This line over there is man-made.
Yes, I made it. I made it. So it actually implies most direct products are not Lerf. Of course, it really depends on what you think, what that most mean. For me, most groups can interact too. Again, there are definitely many other things, but on the left, probably except this, from here to up to here, everything are fundamental groups of stuff up to dimension 3. So I will only talk about 3 manifold groups here. And graph 3 manifold, probably I won't do this. A little bit weird. Graph 3 manifold groups. It is proved by Maple and Weiss in 2001. Yeah, and this really proves all graph manifolds, 3 manifold groups are not there. And the same thing as here, that has been all of such groups. And there's always a gap between who discovered the first example and who proved everything. So here I will only talk about who proved everything. But so this one you will see the first example will show up just in a second. And there's also some kind of mixed 3 manifold groups. And I guess it is proved, finally it's proved by myself in 2019. Again, the first example was not discovered by me, and I will also talk about it a little bit later. So this is supposed to be a relatively comprehensive list if you only care about stuff up to dimension 3. I mean, not too complex, of course, manifold or graphs. If you do not know what these things are, I will talk just a little bit about them later. But if you look at all these things we have, of course, I will only apply to this guy to a special case. And you look at all of this, then you put all these things together, you will get a theorem. That is, if M is compact, orientable, reducible, and the boundary of M is empty or torus, then the fundamental group is there.
Is of any dimension? No.
Oh, 3. Get 3. It's there if and only if M is geometric. So again, if you were here last week in Nathan's mini course, he has told you about the geometrization. Basically, the geometrization is more or less a classification of manifolds in this category. And the geometrization says you can either it is hyperbolic or separate, or you can do some kind of torus decomposition, or I should say geometric decomposition, that's slightly different. After you do the geometric decomposition, they are either graph manifold or mixed manifold. Graph manifold means all the pieces are separate, and mixed manifold means there at least some piece which is hyperbolic. So this theorem is just so this polycyclic group really just take care of the solvable geometry. And if you put all this together, you get this theorem. Okay, and apparently I will more or less focus about this nullers part, because this is where my work lives. There are 2 questions. One is how to construct a candidate H contained in G. Of course, you can always write down anything. It's a candidate. Then how to construct one which possibly not there, and then how to check H is separable or not. So unfortunately, I will not tell you about the first part. I will only tell you about the second part. The first part is still, if I ever talk about the first part, it still can be some kind of a talk, but that's a little bit more, slightly different flavor. Okay, how to check a subgroup is not separable. Then let's look at the first ever non-separable subgroup in the 3-dimensional manifold world. That is by Juin, torus, Solita in 1987. This was the first non-separable subgroup of a three-manifold group that was discovered. And in their paper, they realized that everything in terms of characterization and so on. So let me first write them down. So this is their group. And yeah, I just changed some of the letters. And their subgroup is generated by T and F T inverse F negative 2T. And I take this, so the subgroup generated by these two letters. Of course, it's I believe it's not really generated. Is it? Probably it is. Anyways, I'm just showing you what does it look like in their case up to changing some letters. But as a topologist, if you only give me this, then I probably cannot tell you anything. So let's see what is three-manifold. It's actually a pretty easy, not easy, pretty simple three-manifold. Let me see. So here, this is your M. It is just you take a circle, you cross a pair of pants. Then we call this guy beta, and we call this guy gamma. And then you do paste the S1 cross beta and S1 cross gamma with beta homomorphism of the torus. And I guess in group theory, that's how of doing an extension. You write down a stable letter and you tell me how to do the conjugation. Then you do T beta T inverse equals gamma and T F T inverse equals gamma F. Oh, what is F? This guy is F. This is one of the circle. So this is F cross the free group generated by beta and gamma. So it's really you do F cross beta and gamma, you free product with T, and then do you quotient by those two relations. So this is the three-manifold. It's a pretty simple three-manifold. It's just S1 cross a page, that's a separate manifold. And you paste the two torus together, and it doesn't match. It doesn't send the fiber to the fiber because it's a gamma times F, so it's not a. The whole thing is not a it's not a separate manifold. It's something called a graph manifold, and it literally lives here.
I think it's a punctured torus one where the circle is monitored, right?
Oh yes. Yeah. It is. Yeah, it's also a surface bundle over the circle, but yeah, but I guess for today we are prefer to look at it. Okay, and how do we construct a map? How do we construct this subgroup? You first take a pant. Let me see. I wanna call this guy C1 and call this guy C2. And the first map this pant to this M. That maps C1 to this C1 to gamma F. Let me see. Where is it? Yes. C1 to gamma F inverse and C2 to beta square F inverse. And you can easily check that after you do this pasting of tori, that maps beta square F inverse to gamma F inverse. So you just do this guy twice, you do this guy inverse, so you get exactly there. And then what you get is really you have a torus, a one punctured torus, probably colors by orange. Give you this map to the. So here you have this H. It's injected in this. So this is their constructed. I just translate everything into topology. And probably I should mention that you have a 1 here. Gamma means gamma to the first power and beta to the second power. This will be important. And if you ask me where is the image of this circle, I can tell you there's definitely something here, but that's not a peripheral element. So if you prefer to see some properly immersed or properly embedded subsurface, this is not something you want. So this curve just goes to something here, but not on the bottom. Okay. So let me try to prove this group is not, this subgroup is not separable for you. So this H contain, but for that BKS example, this H containing G is not there. And to prove something is not separable, you wanna find the element which cannot be distinguished or be separated by finite index subgroup. And you just take G is equal to beta gamma, beta inverse, gamma inverse. It looks pretty easy element. And if you can find such a G prime, you can find finite index in G, such that G is not contained in this G prime and H is contained in this G prime. What can you do? Actually, it implies not only this element doesn't stay in G prime, but also many other things do not stay in G prime. Beta f to nth power does not live in G prime. Because you know this H is really generated by, according to what we have over there, gamma f inverse and beta square f inverse. So if beta to some power lives in G prime and this gamma f inverse lives in G prime, then you just, because f is in the center, you do a commutator, or the f goes away, so you have this. Because not only one element is actually excludes easily many elements. And from here, we can actually do a really simple counting argument or look at some current degree. So here is your one-puncture surface torus. It's mapped into your M. M includes this S1 cross hence, then you do this pasting. And suppose this is your G prime, which is given by some finite cover. Then in this M prime, you can just find a piece which contains this guy. This is R DHD piece in M prime containing this one-puncture torus. So I cannot really draw what it looks like, but it should look like you have a boundary component here, it's a boundary component here, and here something, I don't know, and they should be pasted together. There's one single separate piece. And you call this torus T1, call this guy torus T2, and then you call this guy maybe T1 tilde, you call this guy T2 tilde. So you just look at their fundamental groups and you just look at what is the current. And you will get a calculation. Basically, what you will get is pi 1 of this T1 tilde is generated by gamma H inverse and gamma F inverse and F to some power. So just here you have a separate piece, cover this separate piece, you just look at how many times that is to the cover on the fiber direction, that is in this case. And you will also get pi 1 of T2 tilde is equal to beta square F inverse and F to the case power for the same. Because you have already seen that this beta one time times any F doesn't live in G prime. But you know beta square F inverse lives in this torus. So you can easily get that this should look like this. And these two cases are the same because this is one single separate manifold covering this. And then you actually get a degree of T2 tilde covering T2. Then look at what is the index of this subgroup saying in beta and S. That's equal to 2K. And degree of T1 tilde covering T1 is actually only 1. And this is the proof of this Grothendieck group is not set. And I believe it will be the only proof I will really do today. So if you want to really learn any really proof, then that's the only thing. So this is probably the only proof I will do today. Okay, so basically what I will do is to generalize what I have done, generalize this proof to basically any subgroup of any free manifold. So in the theorem over there, I just talked about compact orientable irreducible manifolds, boundary is empty or union of tori. It depends on what kind of three manifold quality you are. If you are, then it may or may not be all the three manifolds you are interested in. I guess maybe 5 years before, that was the only three manifolds I care about. Then I'm pretty happy with that. But maybe you are not, and you care about manifolds with higher Dirichlet boundary. Then let's think about some more general three manifold. Again, compact, connected, orientable, irreducible with incompressible boundary. So these are probably, up to certain things, these are all three manifolds. Of course, you can have prime decomposition, but that will only give you a free product. And if you care about non-orientable manifolds, then this is only an index 2 subgroup. But if you only care about three manifolds up to index 2 subgroup and the free product decomposition, then actually these are all three manifolds. I want to add a little bit more assumption on it. And one thing is it has a with non-trivial torus decomposition. Because if it's a trivial torus decomposition, that means it is either cipher or aporoidal. And aporoidal actually means it is hyperbolic, but it possibly has infinite hyperbolic volume. It's because I didn't assume the boundary is torus. But anyways, those things still have clear fundamentals because of ego result. So if I only care about whether it's nerf or not, I should have non-trivial torus decomposition. And also, correct?
If your boundary has hygienous surfaces, then you won't be able to separate fiber.
All right, but yeah. But here I allow both cases. And I have not solvable manifold. Yeah, this is the answer. I don't do angular. So if you are familiar with the classical characteristic submanifold, you do both torus and annular. But here I only do torus.
Okay.
Yeah. So these are the manifolds I will work on, and maybe I will call it star. This is a condition on a three manifold, and I will work on such kind of manifold. If you only care about nerf or probably some other things, these are the essential case. And my goal, is to do such a thing is that M3 is satisfied star, and the H is a finitely generated subgroup. And I want to ask whether H is separable. So this is the following step. So, and this is probably the main thing I will do. Okay, now I will do some kind of a sequence of constructions. So this is your manifold, and you will associate with the graph. And probably I will only do it for the BKS example. The manifold is just M. I have it here. And because you have a torus decomposition, so you can do a torus decomposition and you get a dual graph. That is, each piece gives you a vertex and each torus gives you an edge. You get some dual graph. And I guess I will call it gamma of gamma M. So gamma will mean graph for me. It's some random thing. We have no idea of how it's connected. Probably it looks like this. Who knows? But in the BKS example, it is pretty easy. This is just one vertex and one loop. Then I will start with this manifold. I also want to do this H. Then I will take MH. It is just a cover corresponds to H in heaven of M. Because H is infinite in a subgroup, so it is an infinite cover. It is a really complicated thing, at least for me. And then you have a graph. So the tori in this M manifold is pre-image is a bunch of probably tori, probably cylinder, probably plane. We don't know, but anyway, they give you also if you cut MH along those things, and you get a bunch of pieces. You can also draw a graph. But in that case, this graph might be infinite, which even it becomes even more complicated. I don't know what that will look like. Probably it look like this. Who knows? But in the DKS example, this again you have like a circle, and then you have a tree here. Infinite tree. Each vertex has infinite many edges and so on. At least for me, I cannot really handle an infinite graph. It is too complicated for me. And then I take kind of a finite core. It's not a Scott core. Again, because H is finitely generated, so that I can do it. But here I do a finite core is just maybe IMH core, which is contained in it. And it's just given by the union of finitely many pieces in IMH. This is union of finitely many pieces. This is a pi1 isomorphism if you think about the inclusion map. So that means in terms of this graph, I just take a finite subgraph. It definitely includes this triangle you can see is here, but it may also contain something else. Because probably this index, this vertex still contains some natural fundamental group or topology, then maybe you also have this. Maybe for among these guys, nothing gives you some any contribution, and maybe among these guys, they give you some contribution. Who knows? This is finite subgraph. And in this PKS example, you can easily see it actually it's still only this. Everything I have done are more or less classical. You can imagine if you have some experience on three manifolds, these are some things you can always do. And the next step is a little bit more complicated. That is, among this finite graph, I will pick some vertices, pick some edges, and we'll get something which should exist here. I get gamma phi h, which is a further subgraph. Then how do I pick all these vertices? So let's see, we are working here. Let's look at this vertex. Okay, it's actually close that we can verify. Yellow, does it work? Where is red? Okay. Let me try to erase it. Oh, it's too. Let me change to another vertex. This vertex is already. Okay, let's go that vertex. Then this is something, this corresponds to something in this infinite cover. I gave it a name, MHV. It lives in MH, it corresponds to some vertex, I call it V. And it covers something here, probably this, called MV. And how do I pick vertices? Then you have MVH, which is the current space of MV, which is usually it's an infinite cover. And I pick it, it's one of the following things happen. Either MV is finite volume hyperbolic. There's something here. I want it to be finite volume hyperbolic, and MVH corresponds corresponds to a motor fiber subgroup. That basically means MHV is a surface cross R. It covers this sigma V cross the interval, and then you pick top and bottom by a pseudo-norm of map. And then this guy covers this V by a set. And I guess if you are in geometric group theory, then this is just those things in a three-manifold group, hyperbolic three-manifold group that are not convex. Okay, it's really like a lot of work on hyperbolic three-manifold. And for experts, I guess I'm hitting a little bit. Then it might be a twisted product if sigma v is not orientable, but let's not assume this. Or if MV is ciphered and MHV has a induced S1 bundle structure. Oh no, R bundle structure. No, ciphered manifold is basically a circle bundle over surface. Then if you take a current space, it is either a circle bundle or a line bundle. Then I only care about the case that this is a real R bundle. Then MHV again, basically the same thing happens, but probably I will do a little bit different notation. Anyway, I won't go there. But in this case, with SV, I use a slightly different notation because this SV might be a non-compact surface. And then we take a car, sigma v here. So for example, SV maybe look like this. Then I don't know, it may look like this. And because SV can be non-compact, so it can be many things here. But what I do is that I take the compact part. Oh no, not here, probably here. So among all these vertices, I just pick some vertices according to that rule. So probably I guess some vertices, maybe I got these 3 vertex and maybe one more, according as you can shape this picture up. And then you can also try to think about how to pick edges. That if if you have an edge, you have 2 things come from the left and right, and if both if sigma v1 and sigma v2 both. So here I'm going a case that this SV is really has a boundary here. It's probably this sigma v, this compact core really stays in the kind of interior of SV. It doesn't intersect with any boundary component. That's totally possible. In that case, you do not pick that edge. Then probably this is just your graph. And probably it is disconnected. And then here, what you can do is you can paste all this sigma v together to get a surface. I guess it is called phi h. In certain cases, not a very good surface. It is probably disconnected. It's probably not proper, but anyways, it's a surface. Again, in the BKS example, it's just that torus. It's still that one puncture torus, and you still see this graph. Okay, this is the whole construction, which is a little bit complicated. And I guess what I can tell you is that with the theorem, M3 satisfies this, and H is a finitely generated subgroup. And then there is a canonical homomorphism S from the first homology of that graph to the rational numbers, but you take all the positive rational numbers and you take the operator to be the product. And then H is separable if and only if S is fixed.
What is it greater than
It really depends on what is your just take all positive rational.
And that's what's sort of algebraic option.
Yeah, with multiplication. Oh, I forget to mention, this is really based on previous work of Yi Liu, who that basically he did all these constructions in the case that H comes from a surface. And in that work, he really think about all the non-zero rationals because he also care about the orientation stuff, but it's just too complicated for me, so I forget about orientations. So I have tell you most of things except what it is S, but apparently I will not tell you what it is. And what I will only tell you is that in this case, you know, it's just a circle. And so this H1 from this guy to all the positive rationals. Then it will just map this one to either 2 or a half. It really depends on how you take the orientations and the other stuff. And really, this 2 or 2.5 really come from this 1 and 2 here. I mean, yeah.
In general,
Sorry?
Your general theorem says that you have a homomorphism to Q.
Yes.
So,
Yeah.
so are there in the general surface construction that you outlined here, is there a general P and a general Q?
Yeah. Yeah, it can be, yes.
And those are the integers that get into your homomorphism. I'm just trying to ask you if there a little more about.
Oh yeah, this is this is really a graph manifold case. In the hyperbolic case, if the hyperbolic pieces are involved, it gets a little bit more complicated. But really, you can look at this 1 is really equal to the intersection number of C1 with the fiber, and this 2 is equal to C2 intersect with the fiber. And up to, yeah. I guess I promised some applications in plural form, but apparently I can only tell you one thing. Something about profound completeness. You have already heard from Martin and Juin on Tuesday about profound completions. You will also hear more tomorrow. So let me talk a little bit about Grothendieck rigidity. So Martin have told you what is definition, but I guess I will repeat it again in case you forget. And it is relatively easier than the profound rigidity because there's definitely a homomorphism on the Eurogroup level. We say G is Grothendieck rigid if for any finitely generated subgroup H contained in G, they're not the same. There's an inclusion map. Then after you write down the inclusion from H to G, you can add a hat to everything. Then you want to estimate not and isomorphism. If you do not have a hat, then definitely it's not isomorphism because I assume it's not the whole. You want this really add a hat is still code. And this is equivalent to something slightly more elementary, and that there's a finite group Q such that you think about all the homomorphisms from G to Q to all the homomorphisms from H to Q is not a bad gesture.
It's not an isomorphism I have, or not a on, or maybe it's the same.
Not isomorphism. Yeah, so there's definitely examples which groups are not Grothendieck rigid by two works, Plekhanov and Hoang. They think about finitely generated subgroup, and Martin and the Grothendieck, they really construct some H which is finitely presented, but still make it to be isomorphic. So probably I will not write them down because of time. And I mostly care about three manifolds, and so maybe I will write down some theorem on three manifolds, which is long and read in 2000. 11, and by Lu and Stephen Fredo in 2019, he said that pi 1 of M3 is Grothendieck rigid. It's geometric, which is long range result, and basically, among other usual assumptions, boundary is equal to empty or union of torus. Usual assumption, I mean, compact connected, irreducible. That's it. And what I can do is really erase all these assumptions. What I could prove, okay, the proof is really in 2021, but it was published this year, is that any finitely generated fundamental group of finite thought is Grothendieck rigid. So how to prove it and why it is related to what I have talked about for 40-something minutes, is that here is a very easy lemma. If H is contained in G, it is separable, then this homomorphism is not untrue. So if you know out of definition, this is only a few lines. It is pretty elementary, and I learned this from long range paper. But this is a very good lemma. It implies all Lerf groups are Grothendieck rigid, because both Lerf and the Grothendieck rigidity only consider finitely generated subgroups. And this lemma tells you if you Lerf, everything are not untrue. And then this theorem really helps you to take care of the non-separable subgroups. Probably I will only show what happens in this case. You see if there's a triangle over there. So in the BKS example, you'll see H0, which is that the Hant group, which is indexed into H. This is a one-factor torus group, and it also they are indexed into D, which is three-manifold group. And they are pretty good. And you can easily check that the normalizer of H0 in H is itself, but the normalizer of H0 in G is pretty good. It is pretty big. It is basically pi 1 of this torus cross 30. But I mean, it is this torus, not this torus, because the separate fiber definitely commutes with everything, so it lives in the normalizer. So it implies the normalizer contains this H0 as an infinite index subgroup. And then by some separability things, you can actually add all the heads for everything. You can check that if you add a head to this triangle, then you have these two guys are both indexes. And if you know this is isomorphism, then you have a contradiction, because this normalizer is only H0 head, but this normalizer condition tells you infinite index. And this proof really generalized to any non-separable subgroup. I guess I have run out of time, so I'll stop.
An algorithm, or can there be an algorithm which imports and takes a subgroup to decide what is separable or not?
So can I say again?
Well, with an algorithm which takes input and group and subgroup, like a previous group and subgroup, and decide whether that group is separable or not.
I guess there will be some difficulties in the process. You need to construct the current space correspond to this subgroup, which is usually infinite cover, and you also need to figure out what are the kind of the pieces in the core, which at least I don't know how to do that. Yeah, I really have thought about this metadata algorithm to do that, but I don't know how to construct this, how to work with this infinite cover and get the core in the algorithm sense.
Arithmetic revolves and manifold starting dimensions 4 are not low.
Most of them are not there.
Except in certain dimensions they're there.
Yeah, except 7 dimensions, I don't know. All the other things are not there. I mean, 7 dimensional things coming from the octanane.
Yeah.
Everything else is not there.
Everything else is not there.
Yeah.
And so we know that typically geodesic sublatives are separable.
They're separable.
Well, it's worth mentioning, even though you're only interested in three medical groups, it's worth mentioning that the richest class of subgroup separable groups are the locally quasi-convex special groups. And there are many more of them than there are groups. Yeah. But choose your model.
Okay, let's hang on. The plan for we thought that